it's hard to not do math for a really, really long time. So it's always good to kind of get back into it and remember what we're doing. We are going to start chapter 7. So chapter 7 is all about exponential functions. And yeah, so that's what we're going to talk about. So just kind of a reminder so far, by the end of Algebra 2, basically you've learned all of the different functions that we have in algebra. So what I mean by that is, so this is kind of big picture, right? We have learned, maybe, Desmos wants to cooperate. We have learned about linear functions, which are usually y equals mx plus b, right? And we can make a different m and b. So a linear function is just a line, right? We have learned about quadratic functions, and we spent a lot of time on quadratic functions, especially before break. So a quadratic function is when you have, the general form is y equals ax squared plus bx plus c. There we go. I'm going to go ahead and put in some numbers here so that we have something that looks like a quadratic function, 3 and 5, let's say. There we go. So, and we'll just go ahead and put in some numbers here. There we go. Okay, so these are the two functions that we've learned about so far. We have a linear function, right? And we have, in purple, we have a quadratic function. And those are the two that we've talked about so far. So today, and in chapter 7, what we're going to learn about is a new function type, which is an exponential function. All right, so an exponential function is, well, basically an exponential function is when you have your variable, your x, in the exponent. Okay, so the most kind of general form would be y equals some number, not 3, it could be any number, to the x power. Okay, so this is an exponential function. And you may have heard of these before in your science class. Exponential functions are used a lot in modeling growth and decay. So exponential functions are an important application in science. Has anyone heard the term you're growing exponentially, or that money is growing exponentially before? Aaliyah, you've heard that before? Yeah. Yeah, so it's kind of like a terminology that people use. Let me move around here, sorry. Okay, so let me flip over to the notes here and just kind of point out some exciting features about this exponential function that we're talking about. Okay, so we're growing exponentially means growing really quickly. The exponential function has the general form of some number a times b to the x power. So you can see that this is different than our other two functions, our linear and quadratic, because our x is in the exponent, right? It's usually where we would have x squared or x cubed or whatever it might be. But this is different because our x is up here in the exponent. B is a positive number and it's not 1. Okay, why can't it be 1? Because if it was 1, then we don't really get an exponential function. Okay, and specifically, this is for an exponential growth function is what we're talking about right now. So exponential growth, we'll get in the next section, we'll talk about exponential decay. All right, so if in the really general sense, if your function is f of x equals b to the x power, and b is greater than 1, then any exponential function is going to look like this. It's going to start down here on the negative x's as really small. Actually, when x equals 0, it's always going to equal 1. When x equals 1, it's going to equal b, and then it's going to grow in this exponential way. And I'll break that down, what exactly that means, why those numbers are what they are. So again, if I go back to Desmos, the very, any exponential function, as long as it's greater than 1, 2, 10, 100. Okay, so I'll put these in order. The red is y equals, or f of x equals 2 to the x power. Black is 3 to the x power. Blue is 10 to the x power, and green is 100 to the x power, if I can talk. So you can see they all start, if you look over here at -10, they're all tiny, teeny numbers, right? This is between 0 and 1. At -10, they're all tiny numbers, okay? When x equals 0, they all equal 1. They all equal 1. When x equals 1, they all equal their value that's in here. So for example, in the red curve, if I can get it to click on there, when x equals 1, y equals 2. And on this one, when x equals 1, y equals 3. And then this one would be when x equals 1, y equals 10. Basically, whatever number is being raised to the x power. And if I went way up there, on the 100, you would see that too. So they all have this growth. The bigger the number that's the base number, the faster your exponential growth curve is going to grow. Going to go really fast. Okay, so very, very exciting, right? All right, so let me talk about why these 2 points are true and why they're kind of important to understand. So open it up in Paint here. All right, so let's take y to the, let's just do y to the 2x power. Okay, and let's do y to the 10 to the x power. Okay, so these are 2 exponential growth functions, right? And so what we want to do is we want to look at what happens when x equals 0. What happens when x equals 0? Okay, so when x equals 0, this first equation becomes y equals 2 to the 0 power. Okay, if I can write a 0 on there, 2 to the 0 power. And this equation becomes y equals 10 to the 0 power. So now this is when the last 2 chapters right before break, maybe you've blocked them out in your mind, but the last 2 chapters right before break, we learned a bunch of exponent rules. And that's what, it was important to learn those rules so that we could do this. Okay, so who remembers what is any number to the 0 power? Anton says 1. I agree with Anton. Any number to the 0 power is 1. So you could have 1,000,000 to the 0 power and it's still 1. Okay, so this means that 2 to the 0 power equals 1. So when x equals 0, y equals 1. All right, same here. When we have 10 to the 0 power, that equals 1. So when x equals 0, y equals 1. All right, so that's why on here they show you that in an exponential growth function that has this general kind of form, okay, actually it's this general form. This is always a point that's on our exponential growth function, 0, 1. Because when you put any number to 0, to the 0 power, it's 1. Okay, so that's how that first point comes about. The second kind of interesting point that we want to understand is that when x equals 1, what happens? Okay, so that would be y equals, I'm rusty on my computer writing skills, 2 to the first power. So if my general form, okay, sorry, let's finish this up. So what is 2 to the first power? What's 2 to the first power? It's just 2, right? It's 2 multiplied one time, so it's just 2. So my second point here is at 0, 2. Okay, and then the same here with my orange equation. If I have y equals 10 to the 1 power, okay, that means it just equals 10. Okay, so my point here is at, oops, I wrote that wrong, sorry. Should be at 110. This guy over here should be at 1, 1, 2. Sorry. Okay, so what this is saying is if my general equation is y equals b to the x power, where b is like your base number, right? Whenever you get to x equals 1, your y equals whatever your base is. So that's why over here you see this point is at 1b. Okay, does that make sense why those 2 points can exist on there? You guys still here? Your brain's like, Yes, okay. Oh, yikes, that banged really loud on my thing. All right. Well, hopefully it's going to kind of start clicking. The other thing that has to do with exponential functions that's kind of interesting is over here. I don't think we've talked about this term yet. And that is that the x-axis has an asymptote on the graph. All right, yeah, so we have the definition of what an asymptote is. Funny word. Everybody always laughs when they hear that word, asymptote. So asymptote is a line that a graph gets really, really, really close to, but it never quite hits. Okay, so what that means is let me go back to Desmos here. That's not Desmos. Here's Desmos. Okay, so in my examples of my exponential functions, right? On the right-hand side, it's easy to see that these grow exponentially and they get really big really fast, right? Even my smallest one, y equals 2 to the x power, when I get to x equals 5, I'm all the way up here to almost there. When x equals 5, maybe. There we go. I'm all the way up to 32. So can you imagine when x equals 10 what I'll be at, or when x equals 100 what I'll be at? So these grow really fast, and that's pretty easy to understand because you're multiplying by itself. So when you have, 2 to the 5th power, that's 2 times 2 times 2 times 2, right? If you add one more 2, then you're multiplying it, and it's just growing and growing exponentially. So you can see if you have this one, 10 to the x power, 10 to the 3rd power is 10 times 10 times 10. You can see how quickly that would grow. All right, so that's kind of the right-hand side after we pass over x being positive. But what happens when x is negative over here? You can see when x is negative, it gets really little, really, really fast. So for example, if I have 100 to the negative 1 power, that's 0.01, right? If I have 100 to the negative 5th power, That's 10 times 10 to the negative 10th power. Remember scientific notation? That means it's a really, really small decimal, 0.0000001. I think I said enough zeros. If not, maybe not. But it's a tiny, tiny number, right? If I have 10 to the negative 20 power, oops, sorry, made that up, right? Way out here. And I'm looking at my table, my chart for this. It's a tiny number. It's basically 10 to the negative 40 power. So it's this tiny, tiny number, right? So you can see on the left-hand side of the equation, these numbers get really small really fast because what you're basically talking about is another way to say 100 to the negative 20 power is 1 divided by 100 to the positive 20 power, right? So you're talking about a really, like a 1 divided by a really big number gives you a really small decimal. All right, so why is that important and why do we care? Well, technically, even if I went all the way out here and your calculator at some point just kind of gives up and says it's close enough. But if I zoomed way out on my exponential function and I went to x equals negative 100 or x equals negative 1,000 even, if I kept zooming out, right? Will my exponential function ever be 0? Will it ever hit 0? So your calculator might basically say, yes, it's hit 0, but technically it's never going to hit 0. So even if I go to x equals 100 or 1,000, let's see, let's try it. No, yeah, your calculator gave up at that point. All right. So at some point it's going to say the number is so small that it's 0. No, I'm trying to see how big we can get. No, about 200 is. I'm just trying to see. Okay, we'll just keep it there at negative 100 power. So what I'm trying to explain is that even though your calculator says the answer is 0, technically way out there you have a tiny, tiny decimal that still exists that is true, even if you go out to negative 1,000. So that's why we call this the x-axis, this line, we call the x-axis, we call that an asymptote because our function, our exponential function gets really, 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 really close to 0, but it technically never can be 0. We can never make it 0 or less than 0. So that's why it's called an asymptote. And asymptotes are actually really important in algebra. We're going to be learning about those with other functions as well. Okay. All right. Have I lost you guys? You still with me? We have exponential growth, right? On this side, we're going to get really, really close to 0, but we're never going to quite get to 0. And that means that this line, the x-axis, is called our asymptote. Okay. So now let's do a couple of problems that have to do with exponential functions. So the problems actually are not too bad. And we'll get back to this too. Okay, so the idea here is to be able to graph your function and then to state your domain and your range. Okay, so let's review what those two words mean. Those are also important, right? So domain basically means your x values that are true, and your range means your y values that are true. Okay, so if I want to graph the function, I'm going to use a graphing tool. You don't have to graph it by hand. You could if you wanted, but you don't have to. So the first one is pretty easy. It's y equals 4 to the x power. So just from what we've done today, you should have an idea of what this looks like. Y equals 4 to the x power. And I'm just, excuse me, I'm going to zoom back in a little bit so we can see those distinctive points. So remember, when x equals 0, y equals 1, right? 4 to the 0 power equals 1. And And when x equals 1, y equals 4. So those are our distinguishing characteristics for this graph. Okay, so if I was going to jot this graph down, my graph is not going to look very neat here, guys. I don't even have a straight line. 1, 2, 3, 4, 1. Okay, if I was to graph this, I know that I have a point when x equals 0, y equals 1. When x equals 1, y equals 4. And then my exponential curve is going to start off down here, go up, and then rise exponentially. That is really bad. That's me drawing my exponential function with a mouse. So hopefully yours looks a little better than that. But that's y equals 4 to the x power. Okay. So the second part is to identify or state your domain and your range. Okay. So the domain is what values of x is this function true for? So for this function, x can be any number, right? It can go all the way out as far as I can this way. X can be 0, that's okay. X can get as big as I want. I could do, 4 to the millionth power, and that still would be a value. It would be huge, but it would still be a value. So in this particular example, number 1, the domain, oh, that's a crazy D. The domain would be all real numbers. All real numbers. Okay, you guys see that? Domain is all real numbers. Okay, what about the range? So the range is your y's, right? We know that up here, everything looks good, right? So we know, and we also know that y is never less than 0. Can y ever equal 0? No, right? We established that that's an asymptote of our graph. So y can't ever actually be 0, even though it can be really, really close to 0. Like it could be a crazy small decimal and never can actually, it approaches 0, but it never actually reaches there. So our range is actually y is greater than 0. Okay, so did that make sense? The domain and the range, how we got those? Because this is going to be something doing the domain and range that we're going to be doing for the next few chapters. So I want to make sure that you guys understood how I figured out what the domain and range were. Cool. Practicing your Spanish. Aaliyah, you okay? All right, cool. Okay, so now let's go to the next one. And this one's, of course, going to get a little bit more complicated. If all your problems were like that, that would be nice, wouldn't it? All right, so a little bit more complicated, but still okay. See if I can draw a little better this time. What was I trying to do? Just trying to erase that. That's what I want to do. Okay. So number 2 is Well, sure. Nope, I don't want to draw the box that gets rid of it. Number 2 is y equals 1/2 times 3 to the x power. Okay, so we haven't talked about this yet. We talked about 4 to the x power, 10 to the x power, b to the x power a lot. But what happens if we have a 1/2 out in front? So what I'm going to do is I'm going to graph. This is the general function, y equals 3 to the x power. But what I'm looking for to graph is 1/2 times 3 to the x power. Okay. Oh, there's like the same color, different color. I'm not sure how to make it different. There we go. There we go. Okay, so the red one is kind of the general one that we've been talking about. The blue one we threw in this multiply by 1/2. So what does that do to our graph? Okay, so one thing you'll notice is that before, remember how I just went this whole big thing about when x equals 0, y equals 1, right? That's still true when x equals 0, y equals 1, but now we're multiplying it by 1/2. So 1/2 of 1 is 0.5 or 1/2. So you can see how it actually reduces because this is still 1, but now we're multiplying by 1/2. So it actually makes our exponential function grow a little bit more slowly. Okay, the same thing when x equals 1 before. Okay, sorry, wrong spot. When x equals 1 before, y equals 3. Okay, now when x equals 1, y equals 1/2, 1 and 1/2. So it's taking this red exponential function that we learned about and then multiplying everything by 1/2. So just even though I just kind of finished telling you that it's always at those 2 points, that's when you don't have a number out front that's multiplying it. Okay, just for interesting sake, you guys always love it when we do it a little extra, right? What if instead of multiplying by 1/2, I multiply by 2? So now you can see my original red function is doubled, right? Instead of when x equals 0, y equals 1, when x equals 0, y equals 2. Okay, and then when x equals 1, y equals 3, you would expect this to be when x equals 1, y equals 6, because you doubled it instead of 1/2 it. Okay, so that's how you would graph. Really, we just needed to graph the blue function, but I just wanted you to understand why did it show up like it did. Why does it look like that? Okay, this one I'll be a little bit lazy and I'll do this. Okay. Boom, there's my graph, right? Oh, it doesn't fit on my screen. Did it get big enough? Oh, it did get big enough. There we go. There's my graph for number 2. Actually, it's the blue one that is my graph for number 2. Right, the blue one is my graph for number 2. So now let's talk about what is the domain. That's not what I wanted to do. What is the domain? So your domain, remember, is your x's. So for this blue exponential function, what are all the x's that are possible? Should be all real again, right? There's no x values that are off limits. So all real numbers as my domain. Okay, what about my range? So remember my range is my y's, right? If I go up from 0, it looks like any y is possible, right? But as I get to 0, my function can never quite become 0. And it definitely can't be any y's that are less than 0. So my range, again, is y equals, or y is greater than 0. Okay. So you might be thinking in your head, Mrs. Ross, cool. All the answers to my homework for graphing exponential functions is domain is all real numbers and range is y is greater than 0. There is a little bit of, there are some other functions that are exponential functions that have gotten shifted and moved a little bit. So that's what example number 3 is, of course, right? Got to get a little bit more complicated. So example number 3 is f of x equals 3 to the x plus 1 power plus 2. Okay, so I'm going to leave my 3x up there. I'm going to graph this a couple different ways. I am going to put y equals 3 to the x plus 1 power. Okay, and I'm going to put y equals 3 to the x power plus 2, and then I'm going to put them all together. Okay, what just happened? All of our stuff went crazy, right? Okay, so let's break it down one at a time. My initial curve, my good old y equals 3 to the x power. It's got my point here, 0, 1. At 1, it equals 3. All is good, right? What happens if in my exponent I add 1? So this is inside my function, right? What happens when we add or subtract inside a function? It either shifts up and down or left and right. So let's see what happens. When I add inside my function, it actually shifts my graph, if I can talk, it actually shifts my graph to the left by 1 unit. So do you remember the weird rules where we've talked about this in Algebra II? I think, pretty sure we've talked about it. We've done, yeah, with quadratics, we talked about shifting graphs. Okay, just want to make sure. So when we add inside the function, so this is inside the function, right? Then it does the opposite of what we think. We add and it shifts our graph left. Okay, so now instead of when x equals 0, y equals 1, it's when x equals -1, y equals 1. Okay, and instead of when x equals 1, y equals 3, when x equals 0, y equals 3. So everything has been shifted to the left by 1. If I would have put a negative in here, then it shifts my graph to the right by 1, right? Everything gets basically shifted over to the right by 1. Remember how that's kind of weird that when it's inside the function, and you're adding, you shift the graph to the left. When it's inside the function and you're subtracting, you shift to the right. Okay, so that's the first thing that's happening to our big equation down here. All right, let's look at the other thing isolated. So what if we take our original equation and we add it to outside the function? So inside the function shifts left to right. Outside the function shifts up and down. Okay, so what this does is it actually shifts your whole exponential function up 2 units. Okay, so instead of x equals 0, y equals 1, now it's when x equals 0, y equals 3. It's being added by 3. Okay, and you can kind of see that here. It looks funny on this side because of the way the exponential curve does, but you're basically shifting your graph up by 2. Okay, so then what this is a combination of the two. What this equation is we've shifted our original red curve, we've shifted it to the left by 1, and we've shifted it up by 2. So if you take this spot here, our good old 0, 1, we've shifted it to the left by 1, and my scale is, yeah, If I make it a little smaller, it's easier to see. There we go. I've shifted it to the left by 1, and I've shifted it up by 2. 1, 2. So that's my kind of inflection point, right? Here I've shifted it to the left by 1 and up by 2. So that's how you kind of get from your original curve to this new curve. All right, so now let me turn all these other guys off and let's just talk about this graph. So this is what we were originally supposed to graph. I just wanted to understand how we got there. Okay. If I need to find the domain and the range of this graph, can I do it? And I can, right? All right, so what about the domain? This is number 3 we're talking about. What is the domain of number 3? What x values are true? So the domain, again, is it could be any x that goes way out this way, it could be 0, and it could be any x that goes out this way. So the domain is all real numbers again. So that stayed the same. That's good, right? All real numbers. Okay. What about the range? So the range is your y. Okay. We're good up here, up here, up here, up here. And then when we get to x equals 2, our graph of our exponent flattens out. And it can never quite get to x equals 2. So because we've shifted our graph around a little bit, instead of our asymptote being the x-axis, or sorry, I should say y equals 2. Y equals 2. Instead of our asymptote being the x-axis, now our asymptote is when y equals 2. Right? It can never go below, it can never equal 2, and it can never go below 2. So that means that our range isn't that y is greater than 0. For this particular equation, our range is that y has to be greater than 2. And that's because we've shifted our whole graph up by 2 units with this part here. Okay? So that's how you do it. The graphing part isn't that that difficult, right? But the just kind of understanding the graph and how the things go into it, I think that's just kind of the important part. Okay, so one last thing for this section, and it is this big, crazy looking equation, not to be worried about. Okay, this is called compounding interest. So when you get to exponential functions, one of the applications, like I said, is in science. There's a lot of things that can grow exponentially. I think there's some, I'm gonna totally misquote myself. I think there's bacteria that grow exponentially. It's like, there's 2 bacteria and then they double and blah, blah, blah. Hopefully they're good bacteria, not bad bacteria, right? And there's some limiting factors. Another big application for exponents and exponential functions is how we calculate interest. So do you know what interest is the question. So if you have a bank account, a savings account, some money market account, anything like that, what the idea is that you, with just a general savings account that earns interest, is that you put your money in there and your bank pays you interest for every month or 6 months or a year that you keep your money um, in your savings account. So if you put $100 in and you just keep it in there for a year, you should earn interest on your account. Okay. It also works the other way, where if you borrow money, they can charge you interest on the money that you borrowed. And you have to pay, if you borrow $100, then you have to pay interest on that money. So you're actually paying back more than $100. So interest is a really important thing to understand. I always like to do, at some point in this lesson, it'll probably be when we get back to class, but I always like to talk about what happens since you guys are so young. If you can put money away when you're young, it's amazing how the interest can work on your side, because the longer time that you have for that interest to grow, the more it'll grow, because it does grow exponentially. Okay. Right now, interest rates are really low, so it's kind of a little bit. But even if you get 3% interest in an account, if you have a long period of time to let that money grow, you can grow a lot of money because it grows exponentially. So again, if you're thinking about borrowing money or thinking about saving money, this is the curve that you want to think about. And you don't have a negative part, right? And it's not exactly like this curve. It's a little bit dramatic. But let's just say 1.1. We'll get a little bit more gentle of a curve. But this is what you want to think in your mind when you're thinking, if I borrow money, right? If I borrow $1.20, or if I borrow a certain amount, right? In 5 years, I only have to pay a little bit back more. But if I waited 10 years to pay it off, then I'm like paying way more than I initially paid back. And in 15 years, it's exponentially more. But it also works the other way to the good, right? If you can put away some money here and you have a long time, like you guys are young, you have a long time to keep your money saving, then the idea of exponential growth works to your favor, especially, the longer you can keep it in there, the more it's going to grow your money. So it's just my little real life application of exponential functions. Keep this idea of an exponential function in your mind, because that's really what people are talking about when they're talking about either saving or borrowing money. That's kind of the model that you need to keep in your mind. Okay, off my math soapbox there, right? All right, so what we're going to talk about is a very generic formula for how a bank would calculate your interest on an account. Okay, and we'll talk about a couple of models for this, but this is a very, very common model. And so let's talk about what this is. It's A equals P times 1 plus R over N to the NT power. Clear as mud, right? Totally know what you're talking about. All right, so what this is this is talking about if you've put some money in and you've left it in for some amount of time, how much money do you have, say, after 2 years of keeping your money in the bank? How does your money grow, right? The amount is the amount at the time 2 years later. Principal is a word that's used in finance, and principal basically means your initial amount. So if you're going to save $100 and put it in the bank, that would be what you put in. That's your principal, your initial amount. Okay. R stands for rate of interest. So the interest rate changes over time. In the long ago past, when I was young, interest rates were really high, so it cost a lot to borrow money, but it also earned a lot in the bank. Right now, interest rates are really low, so the rate that you might get is lower. It can fluctuate, but we can kind of estimate a rate. T is the time in years that you've kept your money in the bank, okay? And it's measured in years. So if we're talking about 2 years after you put your $100 in, T would be 2. So it's not like months or anything like that. It's number of years. And then the last letter is N. N is the number of times per year interest is compounded. So this actually, this can vary. And so we can have, you could get your interest, you could earn your interest every day. Your bank could every day pay out your interest, which would be tiny, tiny amounts, but it would pay it out and it would grow daily. Okay. Your bank could compound your interest every month. So once a month, they said, you know, the first month you put in $100 at the beginning, they give you interest for that first month. Then they give you interest for the second month, then the third month. So every month they recalculate how much you have and then it builds. Could calculate it every year. So every year you have the $100 at the beginning of the year, and at the end of the year they recompound it, or they give you your interest at the end of the year. And I'll graph those so you can kind of see how they differ. They're pretty close in how much money you end up with. So that's kind of the general equation. This is kind of one of those plug in and do kind of equations. You know, you just have the equation and you do it. But it's important to understand what are all the factors that go into it. So what I'd like to do is do this problem, and then I want to use a graph to kind of talk about the differences. So, all right, we'll just go over top there. Okay, so this is problem number 4. Okay, so you deposit $2,000. You worked hard all summer. You saved up $2,000. You deposit $2,000 in an account that pays 4% interest. Find the balance after 3 years if the interest is compounded daily. Okay, so what we're going to do is we're going to take this equation and we're going to plug in what we know. Okay, so the $2,000 is your principal. That's your initial amount. So your principal amount is $2,000. It's a crazy dollar sign. $2,000. Okay. That's supposed to be a dollar sign. Okay. So we've got principal P. Okay. The account pays 4% interest. So 4% is your rate. And what I always say about percents is that percents look pretty, but in math, we never actually use them for anything. So percents are pretty, but we always use the decimal or fraction form. So instead of writing 4% interest, we're going to write our rate as 0.04. Okay, so we never actually use percent when we're doing math, just pretty. Okay. Find the balance after 3 years. So 3 years would be the time, and it's the time in years. So T equals 3. Keep it in for 3 years. If your interest is compounded daily, okay, so this is your N. This is the most kind of tricky part. Number of times per year the interest is compounded. Well, if you compound it every day, how many days are in a year? 365 last I checked, right? Yeah, if it's a leap year. 365, we'll do it 0.25, right, to account for a leap year every... No, yeah, I don't know. We'll just do 365. Ah, I didn't know you had a leap year birthday. That's pretty cool, Anton. I was actually thinking about it as I was writing it. I'm like, how do they account for leap years in there? I'll have to look it up. All right, so all of this, now all you're basically doing is you're plugging in. Okay, so you have 2,000 times 1 plus rate, so 0.04 over 365 to the, and then you do n times t power. So 3 times 365. Okay, so if you calculate this out, you'll find out the amount that we have after 3 years. I am going to use my calculator to help me out. So I have $2,000 times 1 plus 0.04 divided by 365 and my parentheses, and it goes to 3 years. 3 years times 365 days. So at the end of 3 years in my bank account, I would have $2,255 basically. If I just kept my money in there and didn't touch it for 3 years. Okay. Just imagine if, so you guys are young, let's say 15, right? Say you could just work one summer and not needed your money and you could stick it away until you turned 40. Okay, so that's 25 years from now. In 25 years, that money that you socked away when you're 15 years old would now be $5,436. Right? Say instead of waiting until you're 40, you just like put it in this bank account and you completely forgot about it, and you waited till you were 60. If you waited till you were 60, that money that you put in when you were 15 years old would be $12,000 and $12,098. All right. So you really had a long time and you're going to wait till you're 80. You would have $26,923. So that's kind of the idea, that longer that you have, the more it's going to grow. All right, we'll go back to our original 3 years though. The last thing I want to show you, we're almost done, is this is when interest was compounded daily. Remember, that's where this 365 comes from. If your interest is calculated monthly, instead you would put a 12 here, right? But you would also put a 12 up here because once a month it's calculated. You can see how close the dollar amounts are after 3 years. Actually, they're the same dollar amount. You just have a little bit of difference in your change, your cents, right? Or let's say if your interest is only calculated once a year. Okay. If your interest is calculated once a year, that's not ideal. You don't earn quite as much money. You're down $5 over 3 years. So ideally, the more that you can get your bank to compound your interest, the better. But if it's a difference between monthly or yearly, it's not that big a deal. Okay, that was a lot for a day back, right? So I do want you guys to work on your homework. Anton asked at the beginning of class, so just do 2 through 20 or 3 through 23 odd and 37. Anton asked if the homework would be due when we get back. Most likely not. It'll be the same process as before. When we finish the chapter, then the homework will be due the next week. So don't wait to do it, but it's not going to be due that first day we get back. So thank you guys all for coming today. I can't wait to see you in person and hear more about your breaks. And yeah, I'll see you guys soon. I'll talk to you next Wednesday, and then we'll have, let's see, let me make sure. We'll talk next Wednesday, and then the following Monday we'll be back at Learning Tree. So thanks, guys. Have a good rest of your week. Thanks. Bye.